The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
Well, good morning. Again, my name is Jose Alvarez. I've been working on this research with Dr. Brenya. Again, I'm going to be trying to achieve a nonlinear modeling parameters for jacketed columns using seismic rehabilitation of reinforced concrete buildings. So the outline will cover 4 main parts, followed by a conclusion. The first, I'm going to give an introduction on jacketed column behavior, specifically columns with 2 distinct materials. Then I'm going to describe the database that I created in order to be able to understand the backbone behavior of these columns and to be able to compare them later on. And then models to capture the strength key parameters of the backbone curves of jacketed columns. And then I'm going to talk about the deformations of these columns at the different levels. So the aim of this research is to develop a methodology to actually model that nonlinear backbone curve that describes the retrofitted column behavior. This has to be based on, like in other experimental results, based on laboratory test results, based on modifications from existing models, and has to be practical, has to be easy to use in the by a practicing engineer. So in order to do this, this seismic rehabilitation using jackets has been used for quite some time, as we saw for the presentation that we just saw. They're easy to place over existing columns. They maintain column dimensions, so they don't have a significant architectural impact on the structure. And on the structural aspect of it, that increase displacement ductility and strength, and they fix efficiencies in the columns, such as low shear strength, insufficient last splice, and insufficient confinement. Oh, sorry. This over here, I showed 2 responses of 2 columns. The one on the left is unretrofitted column, and the one on the right is a retrofitted column with a jacket. As you can see, there's a significant increase in both the ductility and the strength of the column. So in order to be able to describe this, I created a database based on experimental results published from other experiments that tested the columns under cyclic static loading and presented their results in this manner or in backbone curves. They tested in either cantilever or fixed peak condition, trying to model either frame structures or bridge structures. And the materials that we're going to discuss here today are fiber reinforced polymers, otherwise known as FRP, and steel jackets. I'm not going to mention concrete jackets in this level because they're labor intensive in the field, plus they add a significant amount of mass to the structure. Out of all those columns, I have 146 columns, from which 52 are circular columns and 94 are rectangular columns. And over here I show the distributions between the retrofitted material and the sectional geometry. So these experiments targeted specific deficiencies inside the design of the column. One of them will be low shear strength, which we can see a figure over here of a column that was tested to shear failure. It failed before displacement ductility of 2, which is considered a breeder failure. Inadequate confinement of the longitudinal bars. After the concrete spalls a little bit, the concrete fails, and we can see a failure over here, again, from experimental tests. And a short last splice within specifically the plastic hinge region, which is a common practice in earlier years. We can see the failure at the bottom of the column. And then again, I show the distribution of the the different deficiencies within the database. So to construct these backbone curves from the experimental results, from the published experimental results, we took a two-step approach. First, we extracted the backbone curve of the hysteretic response if it wasn't reported already as a backbone curve. And then from that, we extracted key nonlinear parameters, the yield, the peak, and the residual strength levels and the coordinates of this as shown in this figure. And for the more commonly known, the ASCE values of plastic parameters A, B, and the residual strength C. Over here is an example. We got the hysteretic response. From that, we marked and obtained the backbone curve. And from that, we obtained all the nonlinear key parameters, the yield, the peak, and the residual strength. The peak is just the maximum strength developed by the column. The residual, and for retrofitted column studied in the experiments by that time, they didn't study the columns up to failure, axial failure. So we assumed the residual strength to be 20% of its peak lateral strength, which is conservative, but it's something we don't have this information as of today. For the year value, we used an equivalent stiffness and a horizontal line drawn at either 70 or 80% of the peak lateral strength. And where these two lines intersect, we get the coordinates for the yield strength of the column. Now for the plastic parameters A and B, the A is defined as, Professor Ganoum defined it as the distance, the deformation between yield and the point where the column degrades 20% of its lateral peak strength, while B is the point at which the column degrades, loses its axial capacity. So this will be a more commonly backbone curve from a retrofitted element. And as you can see, in most cases, they didn't test it past a degradation of 20%, or even reach the degradation of 20%. So in those cases, A was taken as a maximum deformation, and B wasn't reported. But C was still taken as the 20% of its peak lateral strength. Now these are four simplified backbone curves obtained randomly from the database. As you can see, 3 out of these 4 curves have vertical lines at the end, meaning that they didn't degrade past the 20%. So this, after normalizing all these backbone curves by the yield strength, we obtain these mean backbone curves from all the columns in the database. As you can see, the drift ratios of these columns, or the mean normalized columns, exceed 5% drift, which is a really ductile behavior. It's really nice behavior. And so on observation, so as an observation from all these database, all columns, retrofitted column, exhibit higher displacement utility, even with the simplest retrofitting scheme. Each retrofit scheme and the details of it was mostly tested once, so it's really hard to catch any outliers in this type of test. Some jacketed columns exhibit gradual strength degradation after low amount of displacement utility, and this will I'll note this again later, and you'll see how this affects the way to capture these backbone curves. And just as another we mentioned again, columns did not exceed 20% degradation, so the actual strength at this level should be around here and not all the way here. This is just the way that we constructed the backbone curves. So now that we have simplified backbone curves from the hysteretic response of columns, I'm going to try to explain how to, from a detail of a design of a jacketed column, get these simplified backbone curves, meaning the thickness of the jacket, the properties of the jacket, how it's placed, and the rebar placing, etc. And with that, we can obtain the backbone behavior. So first, these jackets are placed on the columns at either a section of it or just through the whole length of the column, because they target specific deficiencies through the column. So after they fix that deficiency, the column behavior can be analyzed as a sectional analysis, such as a moment curvature analysis. And we're going to address it this way. So one of the highest benefits of jacketing a column, retrofitting it this way, is the confinement. So this confinement essentially adds the degree of strength that can be developed on the stresses that can be developed on the section, as well as the strains. It controls dilations through the column, so it prevents crack propagation that could create shear failures, and clamps the section. This clamping can prevent the last splice from slipping in the plastic hinge regions. So if we are able to model this confinement accurately, or to some degree of accuracy, we can actually model the jacketed column behavior. So these are the models that I use for calculating the lateral confining stresses. I use the models presented by Priestley for steel jackets, and by the ones presented in the ACI 440 for the FRP jackets. As a confinement by closely spaced hoops, the confinement depends on the properties of the confining material and then dimensions of the columns. And we can see this over here by having the jacketed properties on the top and the dimensions on the column on the bottom. For circular jackets, we know that the confinement is distributed equally through the section. But for rectangular jacket, the confinement degrades. The confinement efficiency gets lower as the height to width ratio of the section increases. Also, it's a common practice to use equivalent section dimensions to try to accurately calculate the rectangular section type of confinement. So for steel jackets, Priestley uses an elliptical sections, and I'm going to discuss how to obtain these elliptical properties later. And the FRP jackets use the ACI proposes an equivalent diameter to capture the lateral confining stress. So these are the models. I created these equations to create an elliptical section that has the area of the original column, and this is to be used in the Priestley model to calculate the lateral confining stresses, and it presents good results so far. And for the ACI 440, they use an equivalent diameter, which is encases the column completely from corner to corner. Then they add a reduction factor to calculate this effective confining area. So this confinement is it's key, but now to simplify it even more, we can use an equivalent transfer reinforcement to theoretically model the confinement provided by the steel jacket in so that we can use the Mander model, which is more commonly used in commercial software, to actually capture this confinement. So to make it even simpler, we take the jacket properties, we calculate the lateral confining stresses with the models that I presented before, and then we take the Mander model. We assume a hoop size and clear for the spacing, which will give us a theoretical confinement equal to that of the jacket. In this case, I use number 3 because it's theoretical confinement. Technically, we can use any available size. So after we get that lateral confining stresses, we can use moment curvature analysis, and this is the uniaxial properties that we have to apply to it. As we know, the core is confined. The inner core of the column will be confined, and we're going to use the confined concrete properties. But because the jacket is an external element, the cover will be also confined. For the longitudinal bars, we use the normal stress strain model, but it was shown on most of the tests that had lapse places, they didn't actually develop the full strength of the bars. So we use the Schoen-Pichera reduction for the stress of the bar. Now, there's something missing that I'm not showing here, which is the jacket contribution to the longitudinal behavior. And I'm not showing this because the jacket essentially doesn't contribute in the longitudinal direction. In the case of FRP jackets, the way they work is that it's a uniaxial material that works in the direction of the strands, which in orienting in, for columns, they orient on the circular direction of the column, so they don't provide in the longitudinal section. But steel jackets, on the other hand, is an isotropic material. When they're placed on the column, they usually leave a gap at the bottom, and if it's a complete jacket, they leave a gap at the bottom and at the top to avoid prying actions when the column is deforming. And also when they're placed, they fill the gap between the jacket and the concrete and the original column. They fill it with some non-shrink grout, and this part poses some slip on the jacket on the longitudinal behavior of it, which makes it so it doesn't contribute on the longitudinal direction. So we did this. We got the spacings. We did the section. This is how it would look on the commercial software that I use. It's called UCS-RC. And it created a moment curvature analysis from which we extracted the peak moments and the yield moments. And using the column geometry, we got the lateral and peak strength. So these are some comparisons with the test. The calculated is on the vertical axis, and the test, the one extracted from experimental result, is on the horizontal. We can see that the model poses a good agreement with what's actually happening on columns, except for some outliers over here. And then for the rectangular columns, again, it proposes a good calculations for these yield values. And then again, we have a few outliers that may be due to some other things that we will have to study further. Now for the peak values, again, it has a good agreement with the calculated values. And again, for the rectangular columns, there's still a few outliers that we have to study more. But the model proposed can actually calculate the yield and the peak value to some degree of accuracy. So now that we have these strength values, we're lacking deformations. And there's two current ways to capture deformations for columns that we're going to do on the field. The first one is get a column that it's on the scale that can be compared to the one that you're going to use in the field, or which is in the same relationship, do a test of a column on the scale that you're going to use in the field, which this was actually presented yesterday in one of the presentations. And the other thing that we use is for existing columns is use the ASCE 41 tables. And we use that for a lot of existing columns. So we're going to use this, but we're going to use the ASCE tables. But because we lack some of the values, we're going to use the equivalent transfer reinforcement used before to actually capture these deformations. So these are 6 columns that I obtained the backbone curves using the ASCE 41 tables, and they're plotted against the backbone counterparts from the columns. The strength calculated here was using the method proposed before, and so the three on the top has the best behavior. They have a full jacket, and they essentially experience the best behavior that we can expect for a column, and then the ones on the bottom are not as pretty as the one on the top. So we can see that the model agrees really nicely with some columns, but then other columns which has it starts to degrade at earlier levels, like the thing that I mentioned at the beginning, that earlier low displacement utility levels, the column starts to degrade. Those columns are harder to capture, so there some more study has to be done on this level for these columns. So conclusion, FRP and steel jackets can fix deficiencies, such as low shear strength, inadequate confinement, and short last places. The majority of columns have not been tested for a degradation greater than 20%, which means that our assumptions on the actual axial collapse will be conservative. The peak lateral strength and the yield strength of the column can be estimated using a sectional analysis. And furthermore, that estimation can be done using equivalent properties using an equivalent transfer reinforcement. Also, the ACE tables can be used using this process, using this equivalent transfer reinforcement to calculate deformations, but I'll suggest some caution on that area. I'd like to thank ACI, NSF, and the University of Massachusetts for funding this research. And thank you very much. I'll be happy to answer some questions.